We left off last time wondering why this isn't a power series. Hopefully you figured it out, right? It's not a power series because it has negative powers. Well, I can't even read my own writing. Negative powers of z. That's not a power series. And so this brings us to the next thing that we want to talk about, and that's Laurent series. So before we do that, I want to give you a little visual picture here that I drew. Maybe I'm hungry because this is what came to my mind when I was thinking about this. But when you're thinking about Taylor series, I want you to think about disks, about pancakes, if you will. You've centered at Z0, you've got radius r, and you've got an open disk around your point. When we think about Laurent series, I want you to think about donuts. We often will call these an annulus. And it might be that you only delete a point, but there's a point deleted and then a region around that point on which you're analytic. So here I want my function to be analytic on the entire disk, then I can write a Taylor series down. To be able to write a Laurent series down, I need my function to be analytic on an annulus, and then I can write down a Laurent series. So a Laurent series, as it turns out, is just a power series combined with another power series in terms of negative powers of z. So you have positive powers of z and negative powers of z. And that's what we're going to be exploring. So let's look at the theorem. This is Laurent's theorem, or I'll just call it the Laurent series theorem. So if you're analytic throughout an annular domain, and again, by the way, I'm saying that z minus z naught has to be bigger than 0. Maybe it's just deleting 0. Maybe you're deleting a disk around 0, whatever, and then we're going to be less than R2. If that's the case, and I'm centered at z naught, then you have a unique Laurent series representation on this annular domain. And here it is. So it's f of z equals the sum, n equals 0 to infinity, of a sub n, z minus z naught to the n. That's the positive powers part. See, n is going from 0 to infinity, positive powers of n. Then you have the other part. We'll start this one at 1. N goes from 1 to infinity of b sub n over z minus z naught to the n. Here's the negative powers part. So I have a unique Laurent series representation on my annular domain, and it looks like that. There's more, a little crazy, but it turns out that we can specifically describe what these coefficients are. And this is kind of the heartbeat of some deep complex analysis theory, which we're going to be exploring in this section and the next. So I'll just mention it now. This coefficient a sub n, each a sub n is actually 1 over 2 pi I integral over c of f of z divided by z minus z naught to the n plus 1. Gosh, that feels familiar. And I need a dz. And then n goes from 0, 1, 2, so on and so forth. That's the a n's. The b n's, what are they? Well, they're 1 over 2 pi I integral over c f of z, z minus z naught to the minus n plus 1. And this is n equals 1, 2, 3, so on and so forth. I should tell you what c is. So c is any positively oriented, simple, closed contour in our annular region. I guess I'll rewrite it. It looks like that. So that is Laurent's theorem, and we're going to take some time and explore that, but I'll stop the video here before we go on.